pleasure is to introduce Professor Alexander Yong from Illinois. He talks about Schubert calculus by root datum and sliding force.
Thank you, organizers, for the honor of speaking here. I'll be talking about joint work that I'm doing with Dominic Searles, who's also at the University of Illinois, and Hugh Thomas, who's at the University of New Brunswick. So I'd like to continue the conversation that Anders started this morning about the old problem. If you have a generalized flag by G mod P, how do you determine laws for the Schubert structure constants? This universal coefficients. Not only in cohomology, but even for some other generalized cohomology theories. Now, I want to emphasize at the beginning that I'm at the very back end line of a long line of people who work on this problem, and I'll try to name as many as I can, but if I forget anyone I didn't mean to, it's really unintentional. So this positivity problem, giving a positive law, has had a bunch of frameworks. There's many ways to calculate these numbers with signs, and there are fewer ways to calculate them without signs, and I just want to name three of them that at least came to mind. So the first one would be Schubert polynomials, as introduced by last student Berger. And one way in which you can think of it is that they are analogs of the Schubert polynomials. So we have full control of the situation. We're very happy in that Grossmannian situation. Another approach that's probably a little bit less well known, although it was better known maybe 10 years ago, is due to Fomin and Krylov. And their idea was to embed the cohomology of flag variety inside a non-commutative algebra with quadratic relations. And in their idea, the positivity problem could be constructed as a calculation in this non-commutative algebra that you could somehow use these relations, these very simple relations on their own, to take a Schubert polynomial expressed in certain non-commutative elements and re-express them positively, then you would have solved the positivity problem for the flag variety. And since then, there's been extended work moving this idea to other types, as well as to other homology rings such as K theory. The third one that was mentioned earlier on by Anders was that of geometric degeneration. That Ravi-Vakil first brought that idea, which in some sense is an old idea, but he re-brought it in. And as a result, you obtain a rule that he stated for checkers, and then Izet Koshkun further developed that idea in terms of Mondrian tableau, and Alan Knudsen, I believe last week, would have described how these geometric degeneration ideas also concern puzzles. So in this talk, I'd like to start again on this problem and avoid these methods and just discuss from the beginning a particular approach, a naive approach to the problem. And nothing I'm about to say in this naive approach is particularly new. It's all been known before, and it's all just exposition. So here we go. You have this G mod P, and you have G, and you have a collection of roots, the positive and negative roots. And associated to your parabolic subgroup P is, depending on how you want to think of it, certain nodes of the Dickin diagram or certain simple roots associated to those nodes. And so the Schubert variety, I'm going to, so the normal way in which you talk about this, if you look into a textbook, is to say, well, Schubert varieties x lambda inside your generalized flag variety G mod P are indexed by cosets in the Weyl group mod this parabolic Weyl group. And another way to sort of think of this representation is that you can take a minimal length coset representative of this coset and then talk about that as indexing it. And that's usually what we talk about when we speak about Grossmannian permutations, if that comes up. So I'd like to discuss a slightly different way of thinking of this. Every collection of W lambda, this minimal length coset representative, you can look at the inversion set. You can look at the collection of positive roots that are turned negative by this permutation or this Weyl group. And what I'm going to do is observe that the poset of positive roots, poset of positives rated by height, has a subposet that I'll call lambda G mod P, which is going to be all positive roots, which are a linear combination of those simple roots that define your parabolic subgroup. Okay? And these inversions, the inversions of this minimal length coset representative are contained inside here. And so just for the purpose of terminology, let me call this these subsets. All the subsets you obtain this way, root theoretic Young diagrams. Okay. And so the naive theme or question or thesis of this talk is there, or what efficacy is there in studying Schubert calculus starting from this collection of objects? So very naive. So the reason why I want to call these root theoretic Young diagrams, because in type A and the well-known Grassmannian case, they are Young diagrams. So in this picture here, this triangle is the poset of positive roots, and if I look at the Grassmannian corresponding to that node that's labeled K, then this lambda G mod P is going to be all the black black dots above it. Right? That's what it means to be the Schubert rectangle that we always draw when we're talking about Grassmannian Schubert calculus. And so the usual way of talking about Grassmannian Schubert calculus is you're looking at partitions contained inside this rectangle, but in fact, in this case, they're lower order ideals. So, this question keeps on coming up all the time. Why is the Grassmannian case so special? And there are deeper and less deep answers to this question. But at least from this simple perspective, there's three things that make this situation especially graphical. This lambda G mod P is a planar coset in the Grassmannian case. These lambda, these inversion sets happen to be a lower order ideal. They have to be true always. And finally, Brucha order, the thing which we do to check if a point is inside some particular Schubert variety, is just containment of shapes. So I want to keep in mind those 3 points as we continue the conversation. Okay. So the other element of the conversation that I want to have is this granddaddy of simple laws in algebraic combinatorics. It is the Schützenberger-Girdequin sliding law. And so there is the rule. You imagine locally you have a tableau, A and B's, and if A is smaller than B, you go to the top row, and B is smaller than A, go to the second row of that case. But I'm going to steal from friend Rob Proctor, and I want to give you, just in case you've never actually thought too much about Girdequin, only heard about it briefly, I want to just tell an analogy that he likes to use, and then I'm going to steal this analogy and modify it a little bit because we'll need it. So, so his analogy is that you imagine a corporation, and the corporation is going to be a Young tableau with numbers inside of it. And in that corporation, you have 1, 2, 2, however many numbers are. And what is it? A Young tableau has the conditions that they're strictly increasing along rows and columns. That means number 1, which is at the top right corner, is boss, right? He is the CEO of this company. And 2 maybe is, you know, 1 is vice presidents, 3, 4. And of course, the numbers going down mean that the higher priority people are bossing people who have lower priority. He bosses him and him, he bosses him and maybe her, and so on and so forth. And so in Proctor's viewpoint, what is a skew tableau? A skew tableau is this corporation sends a bunch of its higher up people to a ski trip. Right, and this ski trip has to be an upper order ideal because certainly you're not going to invite this person on the ski trip and not invite the CEO. So you skew out these things over here. And what happens in this ski trip is that they all perish. And so you have that situation. And so now back at the headquarters, you need to figure out who the new CEO is. You need to figure out who bosses who, and so on and so forth. And so we're going to imagine this idealized world that everything is just based on seniority. The lower number means that you're more senior. And so these laws are the obvious laws you would use to decide who gets the job that is left over by a dead person in the bullet. And by seniority.
You guys should publish this in a management journal.
Well, yeah. But so there are many questions that arise out of this. I mean, you do this, and if you do it in some order, maybe I decide this person gets that job first, and then I decide over here. It may depend how you do these things. There's a real well-defined this question. And one of his theorems, Schützenberger, is that it doesn't matter how you do it. Any way of rectifying will end up with the same result. You will end up with the same corporate hierarchy.
And I suggest that it's not Schützenberger order. Schützenberger was writing things in the Cartesian plane.
Don't like to speak backwards.
We also wrote it for general POSAT.
Yes.
So what does this corporate hierarchy have to do with Schubert calculus? Well, one consequence,
You want to be CEO, right?
one consequence of his rule is, of his law, is a little Richardson rule. That if you want to compute the number of points that intersect with Schubert prize indexed by lambda mu mu, that's the number of skew tableau, number of these situations down here, which rectify to a particular corporate hierarchy. So that is one form of his theorem. And in fact, those in the know that I'm lying big time, because really his theorem is better than that. He has another theorem that says, and it's very closely related to the first one, that says that actually I can just pick any corporate hierarchy over here, fix it, and then the law will still give you the same number. Now I say it's merely one consequence because what makes his law so beautiful and the simple law is that it's not only just doing little Richardson coefficients, but actually it really unifies a variety of important tableau algorithms both in and out of Schubert calculus. So what's the plan of analysis of this thesis talking about these Victoria Yong diagrams? So we were motivated by a bunch of results, it being at this long line. So one of them is that a few years ago, Hugh Thomas and I took advantage of the vast knowledge people had developed with the Grossmanian and what are known as the minuscule varieties. And in particular, Rob Proctor, the same Rob Proctor, developed a Jitter-Camp for a more general class of posets. And so what he did was we observed that if you are a minuscule, or if you're a co-minuscule flag variety, which is a particularly simple class of flag varieties that are most Grossmanian-like in some sense, then Schützenberger's rule, the same corporate hierarchy, holds exactly the same. Except that instead of working on a rectangle, and instead of working on partitions, you work on this lambda G mod P, and you work with lower order ideals. Now I say that this theorem is a consequence really of all the things that came before it in a real sense, because, for example, Herbu and Sotile had done work on these spaces with regards to vanishing and horn type statements. And of course, we wouldn't be able to state this sort of theorem without Proctor's result. There's one other thing that I want to mention about this theorem. So I say for co-minuscule, and there's this sort, I don't want to get into the fine details, but there's a dual root system thing, and there's minuscule and co-minuscule. And in fact, the class of minuscule GMOP is almost the same, but the coefficients are going to be different by a power of 2. That involves the short roots, and I'll come back to that. There's even more that really motivates this sort of conversation that I'm trying to have. In, for example, Kemperbu's thesis, he studies root games, and it's, he talks about partial results in vanishing and non-vanishing. And so when you look at the sum of these sort of things, it's natural to try to analyze more Schubert calculus, both in one of two directions. Can we analyze Schubert calculus using these very Yong diagrams by replacing cohomology by equivariant cohomology, K theory, equivariant K theory? Because if this sort of idea of using these things is really feasible, then it should somehow nicely, I don't know what right word is, mutate to these other types of classes. And then the other thing that you would like to address is this theorem is in the co-minuscule space, and I'm stating this naive hypothesis. And if this hypothesis has any hope of being true more generally, we would like to see that actually isn't just a co-minuscule thing, that it isn't really just a Grossmanian thing, that actually extends beyond the Grossmanian case. And so that's the second part of the talk. So I'm going to now begin by discussing the replacement. Number one, replacing cohomology by some of the more general cohomology theories that are standardly analyzed.
I'm sorry. What do you mean by linear extension?
Yes. So what does it mean to be a Yong tableau? Really, a Yong tableau is a linear extension of this poset, right? There's a poset structure on this, the obvious poset structure, and you're labeling numbers. So in this poset theoretic language, you just say linear extension of these lower order ideals. It's a rephrasing of the same thing in an obvious, intended to be obvious way. Okay, so I'd like to first start by talking about K-theory of correspondence. So I'm interested in multiplying Schubert structure sheets. So we need to, the K-theory, as you know, already contains the cohomology. So really what we need to do is introduce a new law of Schubert. And so what is the law that you need? The situation is that in K-theory, the right idea is that you don't use linear extension, you don't use standard Young tableau, but you use increasing tableau. And increasing tableau, I give an example right here. It's going to be a semi-standard tableau, which is strictly increasing along rows and columns. So in terms of a corporate hierarchy thing, that means that every person might have multiple jobs. That number one is not only editor of, I don't know, Annals of Math, but it's also editor of Convenciones. Right? And so, and that number two is an editor of some other place, somewhere else, and so on and so forth. So, or the corporation, number one may be dealing with accounting and also with human resources. So, what are you going to do when you have this death situation after the plane crash? You have a job opening, and the simplest situation is right here. With these, the corporate CEO has died, and now you have this one guy who's holding two jobs. The answer is that person has to take on the role of CEO, abandoning his previous two jobs, right? And those jobs can later be filled in by entry-level people. We don't actually care. And so that's it, almost. This is essentially the new law. And what I want to emphasize with this new law is that it is not mysterious whatsoever. If you already accept je ne can as natural, then this calculation, one of the smallest calculations you can make, implies that you need this law to be true, that this one person takes on, this one person with two jobs takes on a better job in abandoning his previous jobs. And this is only a slight lie. The more general situation is that you might have a person with many more jobs than just two, and then he may abandon those lower level jobs for many jobs that are better. And with that statement, that's it. And so the theorem that Hugh Thomas and I proved a few years ago is intended to be completely analogous to Schubert-Berger's classical theorem. It says that if I start with an increasing tableau, and because it's a talk, I'm embedding an example into the theorem, forgive me. You start with an increasing tableau like that, of skew shape u slash lambda, and if it k rectifies, meaning that the old law combined with this additional law to this particular superstandard tableau, just like it was in the original case, then it rectifies to that under any order. So this law is more complicated than Schubert-Berger's theorem. Schubert-Berger's theorem says that you can rectify in any order and you'll end up the same way. And what we're saying is that that is not true. It is a false statement, but this is a mild fix, right? So that means, so this is a variation on Schubert-Berger's law that we need. Okay? But even though this is not quite as nice as Schubert-Berger's theorem, what can you do? It is sufficient to prove the following theorem for K-theory. That now K-theory always has the sign attached to it, so you're supposed to ignore the alternation of sign and only focus on the right-hand side. It's the number of increasing tableau of shape u slash lambda k rectified to t mu. And the point of this theorem is that that makes this theorem well-defined as a statement. This was not the first rule for K-theory. Anders Buch provided the first rule that on the subject. But this is a statement that fits inside our particular framework with very Young tableau that we try to extend. So I want to talk about some applications of this new law of K-theory. First, I want to talk about Schubert calculus applications. So some time ago, there was interest in quiver formulas, and so you have maps with vector bundles over a smooth projective variety, and this provides some classes inside that smooth projective variety, the cohomology of the smooth projective variety, as well as the K-theory. And one of the consequences of this kind of line of reasoning became a question. And it's actually a question that goes back to at least the early 1980s. There's a well-known statement in algebraic combinatorics that says the number of reduced words of the long word, W naught, is equal to the number of standard Yong tableau of staircase shape. And to prove that, one can develop something known as Elman-Green correspondence. And so in this paper with Buchprecht, Shimizuno, and Tambakis, we developed a K-theoretic analog of that Elman-Green assertion. And one thing that's true about this, now remember I told you that the nice thing about Girard-Lecan is that it's not only giving a Lorentz rule, but it's also unifying a bunch of tableau algorithms. One well-known statement is that you can actually reformulate at least a p-tableau of Shedstead insertion in terms of Girard-Lecan. And number one is saying that there's a complete analogy in K-theory, that using this additional law, you can turn that algorithm into a statement about Girard-Lecan. The second statement that I want to make is it may be a little bit controversial, but let me state it in the following way. So you have an obvious map between a product of Rossmannians and a bigger Rossmannian. That's called the direct sum map. And so that pulls back. And it pulls back at the level of homology or K-theory. And that means that you get an expression that pulls back a Schubert structure sheet over here into a sum of tensor product of Schubert structure sheets over there. Like, kind of. And so you get some structure constants over here. Now, if this was the same in cohomology, then the analogy in terms of symmetric functions would be I take a Schur polynomial that's of course symmetric in all the variables and split it in half. And of course it's symmetric in the first half and the second half. And how do you decompose it as the sum of tensor product of Schur polynomials? And it's in fact true that those structure constants are the Littlewood-Richardson coefficients in cohomology. So usually you think of Littlewood coefficients as product of Schur polynomials, but you could also think about it as this splitting coefficient. So we analyzed this situation at level K-theory, and it's not true, and I believe Anders Buch already had it's not true that the structure constants are the same as the product coefficients. So that changes. But what is my point? My point is that when you look at the Girard-Lecan formula for this that we developed in the paper a couple of years ago, you actually get a Girard-Lecan formula that has full confluence. It actually obeys exactly the naive generalization of Schützenberger's fundamental theorems of Girard-Lecan. So this is a little bit interpretive, but in this sense, K-theory lets us separate the nice property of Girard-Lecan that comes from product of Schur polynomials versus the nice property that's coming from splitting. The other thing that I wanted to say was extensions to other groups. That was our original intention. Right? We didn't want to stay inside type A, we want to talk about these group theoretic diagrams. And so in our original paper on this K-theory thing, we actually stated a conjecture for all minuscule G-mod P's. And the main case, the only case that that's really essential in the classical setting is these orthogonal Rossmannians. And Buch and Ravi Kumar obtained a Pierre formula for this multiplication, and together with Edward Clifford and Hugh Thomas, we combined with the work of Buch and Ravi Kumar, we were able to apply an associativity argument similar in spirit to the one that Buch was describing to give a proof of that statement. So that's a new K-theory rule that comes from this perspective. Now, I said already that we had conjectured a statement for all minuscule, and like what I get to follow what Anders did, it was false, but I did not discover that false statement. It's actually true for all the exceptional types except E7. And so in E7, Buch and Samuels find the counterexample and fix the statement. So as I understand their statement, it's the same law, but you use a different target tableau than we had originally assumed. Those are some Schubert calculus applications. Now, I want to just point out number one again. So that was Hackett insertion algorithm, and it's sort of an analogy with Robinson-Shensted. So now let me tell you about two non-Schubert calculus applications of this law. So the first application is to the longest strictly increasing subsequence problem. So this is a classical problem that Locke will trace back to Oolong of atomic Bonk fame. So the question that he wanted to ask was that if you take a random permutation, uniformly at random, what is the longest increasing subsequence? What's the expectation of the longest increasing subsequence? So again, that's a random variable, what's its expectation? And many people worked on it, and part of the analysis that led to eventual solution to that problem went through Shenstein. The Shenstein showed, and we all know, people who study this sort of thing, that the length and longest of the first row is in fact the longest increasing subsequence of permutation. And so in the paper with Thomas, we extend that using this Edelman-Green K-theory Hecke insertion algorithm that I developed with Book et al. And we generalize Shenstein's statement. And one of the end consequences of this is that whereas the original problem Oolong has the answer of 2 square root n, we are able to obtain answers for what, if you have a random word, what is the longest strictly increasing subsequence. So it's an analogy to that problem. That was with Ofer Zaitouni. Something that Oliver Peshnik has done is he's used this K-Jirikan and promotion to give a new instance of the phenomenon civic due to Reiner, Stanton, and White. So those 4 Schubert calculus applications together with 2 non-Schubert calculus applications. Okay, so now I want to move on to equilibrium cohomology of Rosmanians. So here we have that they're not Schubert structure constants, they're Schubert structure polynomials, these E lambda mu nu. And so this problem, whereas the original Schubert calculus on Rosmanians was Schur polynomials, the equivariant Schubert structure constants are really the calculation is governed by things called factorial Schur polynomials, which were studied in fact by Lascaux in 1974, but in more modern language that uses the word factorial, perhaps, by these fellows, Eden, Harn, and Look, McDonald, and Green. So they developed semi-standard tableau formulas for these things, and you could use them just like you use Schur polynomials to calculate these numbers. Although they did not know, I mean, it's not that they didn't know, but they did not formulate their papers in terms of equivariant Schubert calculus. So it's just to emphasize that these sort of problems are more widespread than Schubert calculus. So in order to study this problem, we introduce edge label tableau. So returning to our CEO situation, what you're imagining here is that you have this plain depth situation, and now you have all these people that were employed, but you also have people on edges. And who are they? They are really potential outside contract employees that are not really in the company, but if they happen to be more suited to the job than the people who are already employed, they get to jump in. Right? They're outside hires. And so what should the standard Jirikan law be? The new law is the obvious one, that if the outside hire is better suited than the internal hire, then the outside hire goes in. That's the new law. And so, right, there's a standard and semi-standard tableau, and this comes up a little bit. So these standard is supposed to be an analogy of standard tableau, meaning that you use every entry exactly once. Whereas here you have possibly multiples of the entries, like the one in the first row occurs twice. And the law for the second tableau is not exactly transparent. It's weakly increasing along rows, strictly increasing along columns. So that's the way it was before. But I forgive any difference along the horizontal strips. So that 5 being to the left of the 2 is not a problem for this theory.
So which square is so the 5 is just associated, not being the third square?
It's associated to the edge below that square that's opened up. Okay. So standard and semi-standard, just like there's a standard and semi-standard theory in the classical situation. And again, what I want to emphasize is that this new law is not mysterious. Because if you do the most simple calculation in equivariant cohomology, box times box giving you box, then you are able to calculate that there's this thing, you get a box. So this means that if you expect the Jirikan law, then you have to skew a box by a box and be able to rectify to get a box. The only way you can imagine doing that is by putting an edge label in. So again, there's no mystery in this law. And with that new law, we have the following kind of statement. Now, remember, equivariant cohomology gives you polynomials, so I need to tell you where the polynomials come from. Imagine that's your Schubert rectangle, and I'm going to attach numbers, the Manhattan distance in some sense, from the southwest corner. And those numbers you can think of as really simple roots. 1 is E1 minus E2, 2 is E2 minus E3, and the usual way of embedding type A root system. Now here is a theorem that we had actually already a couple of years ago, and the statement is that in order to calculate the Eckler and Schubert polynomial, as the coefficient, I guess, then it's going to be a sum of tableaux that rectify to the same T mu, that one particular superstandard target. But sadly, very sadly, we demand that this be under column order. So whereas in K-theory, we had a slightly bad version of Schubert-Berger's law, here we have no law at all. It's just you choose one particular order of things. And it's unsatisfactory. But
So you mean the boxes you choose to slide into have to be
are fixed. It's a fixed degeneration, if you want, like in a sense, right? You have to go in column order from right to left, and there's no choice.
Okay.
So, I mean, choice doesn't matter if you just want to come up with some way of getting the rule, right? And so in 2008, we stated that rule in lectures and so on, that you just take some of this tableau where you attach a weight to every edge label and you multiply the weights associated with those edge labels and sum them up. And this is positive in the sense of Graham, meaning that this will give you a polynomial which is positive in the simple roots. Now, what's the problem? In terms of the theorem, we had one, because there were earlier rules due to Knudsen and Tao, which was mentioned, as well as due to Pryman and Olev, that used a different semi-standard tableau theory. And so we could biject this rule to theirs. But the original purpose of trying to construct a different way of thinking of this was to go to other settings, maybe either co-minuscule instead of Grossmanian, or perhaps higher cohomology theory. So if we're just going to be satisfied with that statement, it was unsatisfactory because it clearly could not generalize because we don't have anything to biject in other situations. So hence our problem. Our problem was, in order to prove this, in order to be able to carry out an associativity type argument, we need a more flexible form of jeu de Dequin. And so the next slide shows the most complicated of these laws. And here they are. Right? So our solution to this is that instead of working with standard, in some sense it's not necessary to work with semi-standard, but let me do it for simplicity. Work with semi-standard tableau, and you have 4 laws. The first law is the old one. It's Schubert-Berger's law for vertically going up. The second law is new. This says that if you have an edge label here, it can split into 2 tableaux. It can either go into that job and acquire a weight, beta of x, which is the weight of that box according to that Manhattan distance scheme, or it can go above. There's a third thing called a resuscitation swap. It says that if you happen to be in this situation where you have R and R equal like that, then you can actually go down. This is new. This is different than any jeu de Dequin that I've seen, that you actually are going the opposite direction from where you normally think to rectify.
So when you say factor B bigger than factor R, you mean if you factor B below the box?
Yes, sorry. That means that B is going to be my box, my number below the box, and then R is going to be the one to its right, so below and right. And so it's saying that if you have a number below the box, this is basically a mutation in some sense of the simple law of jeu de Dequin, of Eckler jeu de Dequin that we had before. Except that now we actually get a formal sum of tableau. That's something a little bit different. And finally, the most complicated of these new laws is going to be a horizontal swap. And I beg your pardon, but I don't want to actually state the 3 rules, although it's not exactly so hard. But I'd rather just do it by example. In this situation, you want to imagine one wants to take over the job. But it's not only that it takes over the job, but it wants to take lots of people with it. Because when you're moving up in life, if you take your administrative assistant and so on. So in that situation, the number 1, 2, and 3 have the same number of each to the right. And so in that setting, somehow we're balanced and we're okay with that, and we bring the 1 up to there and pull the 2 and 3 over. So if you missed what I was saying, here's a non-example. Over here, number 1 gets to move to a new job, but because there are more 1s to the right than 2s, the 2 that used to be following along with him doesn't get to go along the right. One of the consequences of these laws is that you can actually break semi-standardness. So over here, the 1 and 2 goes up like that and leaves a problem, a 2 bullet 1. In the classical theory, this would never happen. That really semi-standardness is in some sense preserved through the whole process. But in this situation, that can happen and you have to deal with it, although it is not too complex. With these new laws, we are able to show that you actually obtain a well-defined algorithm. Starting from a tableau, you apply these laws. You no longer get a single tableau, but you get a formal sum of tableau with coefficients in a polynomial ring. And if you assume that your original tableau is lattice and semi-standard with content mu, then the result of rectifying under these laws is that you will obtain exactly one tableau, which is the highest weight tableau, and you'll obtain garbage.
By that, you mean reverse lattice work?
And yeah, that the number of ones to the right is more than the number of twos, exactly. Yeah, exactly that statement. And so therefore, you can pick off the coefficient that you want, the equivariant coefficient, by looking at the coefficient of the highest weight tableau in this formal sum. And this sounds like a horrible way of calculating numbers, and it is. But fortunately, the third part of the theorem is that you can directly calculate these numbers from the original tableau. So then why should I tell you about this long story? Because with this long story, we are then able to prove, without appeal to previous results, both this statement for the equivariant numbers as well as the one that I called a little bit defective. And so that's what I'm saying up there. So the next thing I want to talk about is a conjecture that we have. So this defective form of equivariant rectification, it's this one right here. Right? I badmouthed it because it doesn't have flexibility. But one thing it does have is simplicity. And so from the simplicity, you can imagine possible generalizations without having to deal with this complexity whatsoever, which is about the proof. So going in that mindset, we have the following generalization of equivariant K-theory. Well, what should the generalization be? I mean, equivariant K-theory includes K-theory and involves equivariant cohomology. So it must use increasing tableau and it must use edge labels as well. And this is true. But that's not the complete truth. The complete truth is that there's one extra condition that you're allowed to star boxes and star labels with star. And there's this italicized condition that if I and I plus 1 appear in a row, only I plus 1 can be starred. And now, with that condition, we have something completely analogous to the equivariant structure constant theorem. We're going to sum over tableau that rectify, sadly, with respect to column order, and we're going to attach essentially the obvious sign to it. Incidentally, this is now in a preprint form, so if there's some detail that you really want to be said, that it's in fact in print on the archive. And you sum in this way, and there's a certain sign that you attach to it, to the star labels and the edge labels. The details are not so essential, but what is essential is that this is positive in the sense of the theorem of Anderson, Griffith, and Miller, who show that there is a certain kind of positivity that occurs for equivariant K-theory and arbitrary G-mod keys. One feature of this conjecture is that it actually obviously specializes to the previous theorems. Equivariant K-theory should specialize to K-theory in an obvious way by turning off features, and it should obviously specialize equivariant cohomology. As far as I know, this is the only conjecture in equivariant K-theory that has that feature. There was an earlier conjecture due to Knudsen and McKeel in 2004, and I believe published as a conjecture in a paper by Schubert and McKeel, the same one that Anders mentioned. Recently, Alan Knudsen used puzzles to solve a different equivariant K-theory problem, one that is the same as this. And last thing I want to say with this is that we hope that we can carry out some of the ideas we had for the flexible equivariant cohomology JITAN to improve this situation. That's still trying. Okay, so all those things essentially concern the Grassmannian or possibly minuscule. And so now I want to address that second question.
So the last few rules were just with Grassmannian.
Except for the K-theory, which we proved for orthogonal Grassmannians, and now I believe it's a full proof for all minuscules. When you combine that result as well as with the work of Samuels and Bugin, Ravi Kumar. but we're still in this nice minuscule setting. So the minuscule setting has the feature that that the root theoretic Young diagrams are still lower order ideals, Brouwer order is still containment, and the poses are still planar. So from the point of view of testing whether this kind of viewpoint on Schubert calculus can be useful, it doesn't do anything. So in order to test the possibility that this is a useful method, we need to go to another class of varieties called the adjoint varieties. There's a couple of ways to talk about adjoint varieties. Perhaps one way to say it is that if you have a representation of G, there's the standard way to associate a homogeneous space is to take a high weight vector and smear it around by G inside the projective space. And that will be a homogeneous space. And you are adjoint if the representation is the adjoint representation of G. There's a root theoretic way to say this. You can talk about the weights associated to P. Again, the Dinkin diagram corresponds that is well known. And if you take a sum of fundamental weights associated to your P, it might be the case that you're actually equal to high root in the highest root. And in that case, you're also called adjoint. And you're coadjoint if you're adjoint to the dual root system. Okay, so there's a classification. You get things like a very boring two-step flag variety, relatively speaking, as well as some orthogonal Grassmann lines that are not minuscule. And there are also exceptional types as well. So unlike the minuscules, there's actually an adjoint variety for every single case of the Cartan classification. So why is it interesting for our theme, our thesis? First of all, none of the three properties I've been harping on are true. It could be that the lambda G mod P is non-planar. And I'll show you an example in a moment. It can be that our root theoretic Young diagram is not a lower order ideal, and it can be that Brouwer order is not containment. So, but in some sense, this is the simplest case from various perspectives where this sort of thing fails. And so, therefore, our problem is to try to understand whether or not we can analyze these things. One combinatorial commonality. There's something called the adjoint node, the highest node. And so here's the example that, in fact, Anders has solved more generally, but in a different language. You take the two-step flag variety associated to that node and that node, and lambda G mod P is just going to be all of these blacked out bullets. So what does a shape look like? A shape will look like this adjoint node up here will either be on or off, and then you're going to have something that looks like projective space over here, projective space over here. And the fact that there's this funny node that can be on or off as well as a lower order ideal is the common feature to adjoint varieties. And so in that sense, it's not too far from the minuscule setting. So here's an example for Grassmannians, the type B post set, or maybe it's C, I'm sorry. And you choose that node. You get something that looks like Grassmannian, two planes in 9 or 10, plus the adjoint node at the very top, which can be on or off. So here's an example of a shape. It looks like a partition, but you also have a node upstairs turned on. So that's the sense in which it's not a lower order ideal, but there you go. One thing I want to emphasize is short roots are going to be in the middle of there. Okay. Now here's the non-planar case for type D. In this situation, you choose that node, and you're going to get this sort of cube in the middle. But otherwise, it's like a carpet and then a higher carpet on top of it and a cube in this middle. And here again is a lower order ideal, but with a node turned on upstairs. And that's what a shape is in this situation. And this cube, this non-planarity of this cube is the only non-planarity that occurs to every adjoint variety. E7, it looks like that, and I can't draw, well, I probably could draw E8, but I couldn't get it fit in, so I'm not going to do it. So we know a lot about the adjoint varieties. The first time I saw this was in a paper by Chaput and Perrin, who studied quantum cohomology. So they're actually studying a more general problem, but they're discussing a slightly more special problem within a more general class. But these facts are sort of known, that the number of nodes in this lambda geometry is odd, that if if the number of nodes is less than 1/2 the size, then the adjoint node is turned off, otherwise it's turned on. If it's greater than 1/2. And you know, if you have a shape that with an off adjoint node and off adjoint node, then Bernard order is containment of lambda mu. But it can have some problems otherwise. So okay, so let me. Here's my summary theorem with Dominic Searles. So let me say it this way. In the minuscule setting, we had already, meaning the community, had already gathered all these wonderful results, and we were able to take advantage of that. In this situation, we don't have as much known. One of the nice theorems of Schubert and Perrin is that they generalize our minuscule result to a setting that implies some of the structure constants for the adjoint varieties. And I'll tell you which ones those are. They're the ones where all the nodes are turned off in both lambda mu and nu. And so the idea that we could use Ruther-Young diagrams, or naive idea, I mean, it works and it doesn't work. One of the ways in which it doesn't work is that we, at present, do not have a group theoretically uniform rule for all adjoint G-mod P's. And we don't even have a Schubert rule. Maybe that's just the way it is, I don't know. But the good news is that when you look at the answer, there are commonalities between various types. Not only commonalities within the adjoint family, but even with the minuscule family. So, for instance, you don't need to look too hard at the things, but in the type A, all the numbers are in fact equal to 1. Of course, this is a special case in some sense of Booth's theorem, but it's stated in a different way. And we can describe exactly which coefficients are 1 and which are 0. In type C, we actually reduce the calculation to a Grossmannian of two planes in some rows. In one situation, if all of them are off, all the nodes are off. Now, interesting case is when you have off, off, and on. This is something that's not covered by earlier results of Chaplin and Perrin. Here you've got a sum of two Grossmannian Lorentzian coefficients in terms of sort of sliding operation involving the adjoint node. And I don't want to get into the details of that.
Could you explain once more on the on and on the off?
Yes. So maybe, so you're going to have sort of three regions. Right? This region up here, this region over here, and this region over here. A shape, it's not arbitrary what you can put on and off, right? But if I have something like this with very few nodes on, maybe I'll make this just the large then this node has to be off. But if I have too many up here, then somehow this must be on. So on and off refers to whether this guy's turned on and off. That's sort of the common feature of adjoint Schubert calculus, or at least the combinatorics. So where was I? So you have this kind of state. Now, what's going on in type B? Type B is going to be the same answer as type C, except you multiply by a power of 2 using the short roots of your, remember, we're working inside a collection of roots, so they are short or long. This is the exact same type of correspondence that occurs in the minuscule case. And finally, type D is the hardest case in our analysis. And I'm only going to talk about the main type because I want to hide the details. But the point here is that it looks very much like type C. And you know that type D, of course, has no short roots, so we have to actually construct what we call fake short roots in order to state this sort of theorem. Okay, so just remarks on the theorem. Earlier work of Schubert and Perrin, in fact, gave Schubert example when lambda mu nu are less than 1/2 the size of the entire coset. Now, what we really have are product rules for each of these classical cases. And the idea is that you know the Lorentz rule for Grossmannian two planes in C, I guess I should say C, 2n, because of the classical Lorentz rule. And you can use that in order to obtain a rule for Lagrangian Grossmannians, except you need to demand a new idea, this adjoint node sliding operation. In order to get one for the most difficult case, the one that involves this non-planarity, then you try to do the usual folding. You sort of squash down and you kind of reduce to the Grassmannian case again, except that you have some ambiguity, because when you squash down, you're projecting, and it can be a 2-to-1 map in some cases. And so a lot of the complication of this rule is really to figure out that disambiguity. So again, it's not a complete testament to the wonderfulness of the thesis, but it is some evidence towards it. Now, these rules actually give us very strong control of the numbers. For example, here is the maximum values that can occur in every one of the adjoint and coadjoint types. Now, in the exceptional types, we actually use a presentation due to Chapeau and Perrin. But in the classical types, we actually know by theorem what the maximum numbers are. In fact, what all the numbers are. In type B and D, I believe they're just powers of 2. So we have very strong control in that sense. Conclusions and summary. So the purpose of this talk was to discuss the idea of combining group datum as well as sliding in order to investigate Schubert calculus and various homology theories. For the Grassmannian case, these sliding methods that extend classical jeu de Caen due to Berger give us a fairly complete understanding up to a conjecture in current K theory. And it's very sort of, the conjectures and the theorems are the inherent properties of lower homology theories in a natural way. And the new laws that are invented are intended to be not mysterious. In the minuscule cases, these methods do show some promise. For K theory, they lead to almost a complete answer in a minuscule setting. And beyond minuscules, we discuss the adjoint varieties as a natural step to test the thesis. And with these statements, this is essentially the entirety of our information towards the thesis, except for one thing that Dominic has shown me. There was a paper due to Bakal and Kumar that talks about what you might consider nice Schubert structure constants. And in work that was mentioned by Anders Booth due to Knudsen Prabhu, they develop a puzzle rule for calculating these numbers. What Dominic has shown me is that you can actually calculate these numbers in terms of the setting. So what is the idea? The idea is, what is the Bakal-Kumar structure constant? Well, here's the positive positive roots. Well, I don't know. It's not bigger. And you're working in a partial flag variety. So partial flag variety says that maybe I'm knocking off this node of the diagram and that node. And so just like the adjoint picture over there, you get 3 regions. And roughly speaking, a root theory Yong diagram is going to consist of a Yong tableau over here, a Yong tableau over here, and a Yong tableau over here. But not all possible ways of putting Yong tableau here are valid. Just like in adjoint setting, that there's this condition on how big the things downstairs are. Now let's suppose we're calculating UVW, the flag variety number. And suppose this is W, and suppose it so happens that U is going to be this boxed out thing over here. It's going to correspond, it's going to have a shape. The inversion set is just going to be these guys over here. And finally, suppose that B this is a statement due to Searles. Suppose it happens that B also consists of shapes that are inside this, and this. Okay? So what you're thinking here is that these are 3 independent classical Literate coefficient calculations. And so then you would just be calculating the number of ways to fill this that gets to this, number of ways to fill that to get to that, number of ways to fill this to get to that, and multiply the answers together. His observation is that those are exactly the Valkelli-Kumar numbers in type A. And so therefore, this is yet another evidence that this root theoretic Yong diagram approach does see the simplicity of those numbers. Thank you.